Hi friends, good evening. Today we are going to do another section of vector analysis, that is different types of coordinate system, right? So here we discuss what is Cartesian coordinate system, what is cylindrical polar coordinate system, what is spherical polar coordinate system, and then we focus on different volume, area, element, how we represent in different types of coordinate system, right? So let us start with the Cartesian coordinate system, right? So different types of coordinate system, right? So today we focusing on Cartesian coordinate system. So Cartesian coordinate system, that we are commonly using coordinate system, right? So you know what is x-axis, y-axis, z-axis in a three-dimensional event description. We usually use a three-dimensional coordinate system, right? So here you can see one coordinate I have given. So this is x and this is y and this is z-axis. So the position of a particular point in a three-dimensional coordinate system, how we represent. So let us check first that, right? See, suppose a particular, this is the, I am representing a point, right? So from the origin, this is our origin vector, alright? So here another point x, y, z, this particular point, right? This point is, or that particular object is fixed at this point, right? That point we can represent x, y, z. This is the position vector, right? Now, how this position vector we represent? So, you know, position vector of p minus position vector of o. That means x minus 0 I cap plus y minus 0 j cap plus z minus 0 k cap. Alright. So this is that position vector r. That is r is equal to xi cap plus yj cap plus z k cap. This position vector representation above in a three-dimensional space to a point P, that is very important, right? So that is r is equal to xi cap plus yj cap plus zk cap. What is this x, y, z? That is the x, y, z coordinate value at that particular point. Alright? Alright. Now, how we represent in Cartesian coordinate system, how we represent a displacement vector. Alright? Let us look at. So, here you can see, here I am considering one x and y coordinate system, right? X, y, right. So, this is my x-axis, this is my y-axis and this is my z-axis, alright. Now look here. Here the position vector, I have represented position, two position vector, right. This is suppose a point A and this is a point B. Then a particle is moving from A to B, right? Then what is the displacement vector, right? What is the displacement vector? That is AB, right? AB is the displacement vector. Now, how we represent using it vector concept? See, you can see this is the position vector to the point A that I taken as r dash here, right? And this vector, position vector to B, here we taken as vector r. Alright? Alright. So, by triangle law, these two sides are in the same order, but this side is in the reverse direction. Right? So, using triangle law, what is the resultant of these two vectors? So, we can write r dash plus r dash vector plus this capital R. Right, that means our displacement vector. Capital R is our displacement vector, that is equal to R. Alright. Then what is our displacement vector R? Capital R is equal to R minus R dash. Alright. Alright. So now what is R? What is R and what is R dash? Let me use this. A is a point of x, y, z, and this B, right? So let me write x dash, y dash, z dash, R dash point, and I can use R point as x, y, z, right? Now what is this displacement vector R? Position vector R minus position vector R dash, alright. So let me write that as R is equal to, right, what is position vector R? That means this vector R, xi cap plus yj cap plus yj cap plus z k cap, right, minus what is position vector R dash? That is x dash I cap plus x y dash j cap plus z dash k cap, alright. Then this displacement vector I can write as R is equal to x minus x dash I cap plus y minus y dash j cap plus z minus z dash k cap, alright. So this is the displacement vector notation in Cartesian coordinate system, alright. So or we can write as, see, let me use another term. Suppose one point, this is x, y, z, right, in a 3 dimension you think, and then a very nearby point, I am considering a very near point. Then what about this point? This is x plus dx, this is y plus dy, and this is z plus dz. So when I am changing from, right, here you can put like this, okay, alright. See, so when I am moving from A to B in a 3 dimension, a small change in x axis length, a small change in y axis length, a small change in z axis length, alright. Then what is this position vector of B minus position vector of A? Then how this displacement vector dr I represent? Dr is equal to x plus dx minus x, that is dx I cap plus y plus dy minus y, that is dy j cap plus dz k cap, alright. So in Cartesian coordinate system we can represent the infinitesimal position vector, or dr is dx I cap plus dy j cap plus dz k cap. How we represent position vector? Position vector R is equal to x I cap plus y j cap plus z k cap, alright. Now to find if once you know position vector, how the position, the point that that position is moving, then velocity you can find as dr by dt, right. Then this is vx, right, dx by dt I cap plus dy by dt j cap plus dz by dt k cap. This all we studied, right. So in Cartesian coordinate system, how we represent a position vector and a infinitesimal position vector, that is dr, how we represent. Now how we represent the area, volume, that all are very important, right. So look here, now let us go to see, suppose I am considering a cube, right. So let me take a 3-dimensional cube, alright, right. Now if I consider 3 axes, alright, suppose along this direction I am taking x axis, right. Now along this direction again I am taking y axis, any axis you can take. Now again I am taking z axis. Okay, right. Now here I am choosing x, right. Here I am choosing y. Here I am choosing z, right. So in a Cartesian coordinate system, one cube we can represent like this. Okay. So cube, this part is origin, right. And here we can use another point x, y, z, right. Now suppose this is this length, right. This is I am representing ax, and this I am representing ay, and this z axis length I am representing az. Alright. Now how I represent this point? That point is, it is at a, this ax is there, ay is there, az is there. From z axis this point is at a distance az. From x axis this point is covered a distance of ax, here ay. So this point we can represent as a is equal to ax I cap plus ay j cap plus az k cap. Alright. Then what is the magnitude of this a? Alright. That means length of that diagonal. Right. So actually this vector from this origin, right. So this diagonal, right, length is root of ax square plus ay square plus az square. Alright. So this kind of information, how we represent a solid in 3-dimensional figure and how we represent coordinates, that all are very important. Alright. Alright. Now let us go to how to represent. See, this we have already discussed how to represent an infinitesimal length in Cartesian coordinate system, or length element. How we can say how we represent length element in Cartesian coordinate system. We already seen dl is equal to dx x cap plus dy y cap plus dz z cap. Alright. Alright. Now area representation. In a Cartesian coordinate system, how we represent area, right? So let me use the area representation, how we represent area. Look here, this is y axis and this is x axis and this is z axis, right? So how we represent area? How we represent this area, right? So what is the direction of this area? This area is projected along. I already told you the area direction is perpendicular to the plane. Suppose we consider a plane, right? Suppose you consider a plane like this, right? So area is perpendicular to this. So this is the area direction, alright? So, or this is the area direction, right? Perpendicular to this plane is our area direction, alright? So any area given, you draw a normal to that surface, that normal direction is the area to that area direction of that surface, alright. So here this is the shaded area I have given, then this y, right, this is y cap direction, alright. Now here how we find, suppose a small length in x axis, x direction is this, so this is dx. So this is z axis, so this small length we can represent dz. So how I can represent this area? Area, small area, dA is equal to, what I can write? That is dx dz y cap, right? dx dz y cap, alright, in the length into breadth. Alright, so that direction is y cap. Now to find the area, full area of this face, what you have to do? Integrate this. When you integrate, but this is a double integral, double integral cube side is varying from 0 to a. Alright, if I am considering both x and z varying from 0 to a, dx dz y cap. Alright, then integral dx is x 0 to a. Integral dz is z 0 to a, that is a into y cap, that is a square y cap. Right. Now if you consider this area, it is parallel to the same this area, right? So that's why, but the direction is, this area is projected in this direction, right? That face is in this direction, this face is that direction, and this face is in this direction. So this is obviously this is y, this is minus y cap. Then here a square minus y cap come, right? Now here if you choose what is the area, right? Here this direction is z cap, right? Z cap, and this length is again, right, dx, but this length is dy, right? So this is dx dy z cap. Then when we integrate this, so this is equal to dA. When you integrate this dA, what you get? 0 to a dx, 0 to a dy, and the direction is z cap. Alright, then what you get? You get this is a, then this also a, then a square z cap, right? Then the down area you can write as a square minus z cap, because the same area downward, right? So this way we can represent area for a particular figure in Cartesian coordinate system, right? Alright, so how we represent area, that is very important. Alright, now volume, how we represent a volume in Cartesian coordinate system. Alright, how we represent a volume in Cartesian coordinate system, right? See, volume is length into breadth into height, right? So you consider a three-dimensional figure, right? So we consider a small volume like this, right? A small volume. So if you consider this as y-axis, then this is dy. Alright, so let me write it. This length I am choosing dy. This length is dy. This length is, this is x-axis, so this is dx, and this is z-axis, so this is dz, right? This height is dz. Then what is length into breadth into height? That means dv is equal to dx into dy into dz. Now to find the full volume, integral 0 to a, for a cube I am considering 0 to a and 0 to a, that means dx dy dz. If it is a cuboid or any other shape, what you have to 0 to L, 0 to B, 0 to H, right? So here I am considering. So x 0 to a, and y 0 to a integrating y, that is again a. dz on integration is z 0 to a, again a, that is a cube, right? So volume element we can represent in Cartesian coordinate system, three-dimensional Cartesian coordinate system, we can represent as dx dy dz. Alright, area element based on the different phase dx dy, dx dz, dy dz, different area elements also will get. Alright, alright. So volume element is, what I can write, a volume element is dx dy dz. Alright. So this is all about a Cartesian coordinate system. This Cartesian coordinate system, we familiar with the Cartesian coordinate system. That's why the discussion is very less. But as far we considered with a cylindrical or a spherical polar coordinate system, we require a lot of discussion. From that part we will encounter more problems in electrodynamics, right? Okay, thank you.